my talk is about tailored firmware emulation. Army of Undead was just, the next best title which would fit into that topic. I have researched all of that stuff at the University of Technology in Vienna. It's called TU Wien, but yeah. And I have done a lot of case studies, which I want to present during this talk at the company I work for, which is SecConsult. It's a company which is acting worldwide. So I'm obviously sitting in the office in Vienna, but we have also a lot of offices in Asia and in North America. And yeah, I have also a lot of colleagues which are doing research and pen testing of embedded devices, firmware, hardware, whatever, in Europe, especially in Europe, but also in Asia. And yeah, that's just a tip of research, what we have done during our work. About me, I'm Thomas. I have spoken at previous conferences in Asia and Europe, also at Hack in the Box last year in the Netherlands. And yeah, you can reach me via this email address. I don't have Twitter, but you can ping me on LinkedIn too, or on Xing, whatever. And yeah, that's it. So the outline, what I will be talking about today is the question, what is the topic about? Because firmware emulation is not the same like firmware emulation. So it can be firmware which is one compiled binary, a little thing, which is burned into a chip without any external memory. But it can also be a whole operating system and not one compiled thing, which includes file systems, which may include some I/O devices and whatever. And yeah, why did I do all this research about firmware, about emulation, and yeah, what is it about? Also, some clues about firmware development, how it is done nowadays, how it was done, and especially all these depending supply chains which are in between. That's a really funny thing because I, as pen tester, and also my colleagues have seen a lot of stuff and a lot of things how firmware was developed, or yeah, how it looked like, how it was developed. And you often find some mistakes, some bugs, some vulnerabilities in one firmware and in completely different firmwares because they may have used the same code, but yeah, that's another thing. And then I want to start with the project I have done, what I want to talk about today about the firmware emulation, the detection of the essential parts. So just how to look into the firmware, how to detect things that you will need during the preparation of this undead firmwares or these fake firmwares. A colleague of mine have called it Frankenstein firmwares, also a funny name. And yeah, then I want to show a little demo. I've prepared some emulated firmware, one firmware which I want to start and where I want to show a small vulnerability that I have found and released with colleagues at the company. And also I will also give you a clue about how to monitor and debug the emulated firmware or the processes in this emulated firmware. so that you can find vulnerabilities and maybe also find blind injections, which are not easy to see from outside. So when you're pen testing a device, you don't know whether your payload was successful or not because you cannot look into the device. That's another advantage that you have when you emulate the firmware. And yeah, I've also done a scale study about almost 200 firmwares from 49 different vendors, but more about that later. And I've also discovered known and unknown vulnerabilities. So the known vulnerabilities, some of them are pretty old, but yeah, they are there still. And yeah, I cannot reveal all of the vulnerabilities that I and we have found during this research because they are not all of them are published now. Some of them are in our responsible disclosure process, so it's not completed yet. But yeah, the vendors know about that, and others of them, because we have discovered too much, are not communicated now. And then I will also give you a clue about how emulation can be improved in the future, and yeah, the conclusion of the whole research that I have done. So what is it? What are the expectations? It's an emulation of Linux-based firmware with a binary interface. So no complete real-time OS like VxWorks, like Ecos, GVOS, TinyOS, whatever. There are a lot of real-time operating systems which are small and which are compiled in one monolithic binary, including all scheduling and binaries and whatever. Windows, which may be interested, but I have also seen one Windows or two Windows firmwares until now, can also be covered with a similar approach, but I have not implemented this in this prototype, in this process which I have built, and yeah, that's maybe future work. It's about dynamic analysis, so this means I've tested libraries, I've tested networked services as far as it was possible. So it was not always doable to start all these network services, but for these which were possible to be started, I've done some analysis and also of non-exploits. So some proof of concept codes from the internet, from Google Project Zero or whatever I've found, and this also during runtime. So I've just started up the firmware, have tried all the exploits, gathered how much ports are open, TCP ports, UDP ports, which processes were started, and so on. And yeah, that was part of the dynamic analysis. It's also a feasibility study about the workflow to realize simple firmware emulation. So it's not a ready-to-use tool. It's not something that I can just push on GitHub. It's just a few lines of script code for pre-analysis, few lines of script code for automating some things, but it's not a whole open source project. It's just a feasibility study. And yeah, something about the outcome. More than 170 firmware images were emulatable across more than 49 vendors. That was impressive. So out of 200, I have not expected that it will work that good. But after some tweaking on scripts, on the workflow, it were really good. But more about the outcome later. And yeah, advisories that have been released based on only emulating the device are really funny, because when you communicate with the vendor, we had one case where the vendor responded that, hey, can you test this and this on the device? And we just say, no, we don't even have the device. So it's just emulation, and we have found a lot of vulnerabilities. And he was just, wow, okay, I have not expected that. But yeah, it's funny, and it's really cool. And the whole project was started in January 2017. So that feasibility study is not a short-term feasibility study. It was done as a long-term feasibility study. Yeah. Why did I do this? So it can be used for doing remote testing with certain frame conditions, which means you can test the complete embedded system without having it. So this was especially cool for our lockdown that we have here in Austria, because I can test devices with frame conditions of customers remote. And yeah, that's really nice. And it was also helpful for past research projects, for past customer projects, where we have done emulation and used it for example, for unpacking, or for doing some binary execution stuff, which you cannot do on your desktop computer because of the architecture and the OS and the kernel and so on. And yeah, currently dynamic analysis is just limited to few architectures like ARM and MIPS. So that were the projects that I have found on the internet about this. And yeah, I wanted to extend this. And also the static analysis, which is well covered by commercial, non-commercial solutions, was another point where I've thought, okay, when static analysis is now that good researched, why don't we have to do dynamic analysis? Why can't we do just let the firmware run on any architecture? And yeah, tools of that, you might know them, are Firmware, Facts, IoT Inspector, and yeah, so on. So nowadays, nobody wants to work twice. Yeah, even any work. So some developers try to do it really, really fast, which means sometimes copying code from other vendors. That's also a point that we have seen during the study. But Buildroot is one of the most handiest tool that I've ever seen for developing embedded systems, and it's really nice. I have also used it during the study. A lot of projects regarding developing of embedded devices are sometimes based on development kits, hardware development kits, software development kits, firmware development kits, sometimes even to integrate cloud communication into the IoT device or into the embedded device, whatever. And some projects, some products are just looking like, yeah, a collection of development kits in one thing from totally different vendors all over the world. And very often they also have all the vulnerabilities inside of all these development kits. That's reality. And that's also because of end of life, time to market, outsourcing, and whatever you can collect whatever buzzwords you can collect about developing firmware, hardware, software. And yeah, we have seen that for many products in the past. For example, this one, the vendor had to contact the OEM to get a fixed firmware for the vulnerability that he had in his product. And yeah, that's a thing. Due to the age of the product, we cannot give you a quick answer and so on. Yeah, cumbersome, but it is how it is. And regarding all the development kits and outsourcing, of course, one vendor we had investigated, a colleague of mine had investigated, was Xiongmai. The vendor had done white labeling. So you could just say, hey, vendor, please print my label on this IP camera, and I can sell it as my own trademark, with my own trademark on it. And yeah, that was done for more than 100 sub-vendors, I think, and was a blog post in in 2018, I think. But yeah, was a big issue. So yeah, who is developing in-house? Who knows? Some words about storage, which is typically used. So embedded systems are using storages like SPI flashes, NAND flashes, SD cards, and so on, which you can see here in the pictures. But it is not that easy to burn it on the chips. So it's often done via a programmer, JTAG, or another debug interface. And yeah, you can also flash it directly for SPI, for example, because it's this small chip on the right side. It's really easy to flash it on it. But for the most of the other things, JTAG is a little bit better. And there is also a part of the memory. Nowadays it's a part of the memory which is called the NVRAM, the non-volatile RAM. It used to be a separate integrated circuit, but now it's often a small partition on a system which is accessed by a kernel module. And that was also a challenge during the setup of the whole emulation framework or emulation scripts, how do you want to call it? But yeah, it's not so often used in new developments, in my experience, but it's present. So there's also a lot about distribution, which was done via websites usually, sometimes via FTP servers, or sometimes when it's special hardware, then you get a physical mail where it's a USB stick, CD, disk, whatever inside. And some vendors also use push messages in the web interface of the device. So for example, Netgear or Ubiquiti, I think, they are using push messages. When you open up the web interface, then you'll get a message where you can see, hey, your firmware is outdated, please upgrade to the latest version by clicking on this button. That's also really nice, but the device needs internet connection, which is not the case for all devices. And yeah, that's some words about distribution. And when you want to upload it for the most of the customer devices, you can do it via the web interface. Just upload the firmware, click on upgrade, wait for the reboot, and that's it. And for other specialized hardware or different hardware, you need to prepare a USB stick or an SD card, and sometimes you can also upload it via TFTP, FTP, and in rare cases, it's just possible by doing it via an external programmer like JTAG, but it's often possible via multiple ways. So that was the thing by that was the device upload and the distribution of firmware is the one thing where you can just get, or sometimes you just get a partial image, not the whole image, which is containing all of the information which is inside of the device. And when you extract it from the device, you can get the whole image of the complete IoT embedded device, whatever. And there is all the information inside that you need to emulate it when it is possible. And this can be done via JTAG, ISP, SVD programmers. When you have programmed an embedded device, you know the stuff, but otherwise you just Google it. And you can also do it via chip-off techniques. So the storage chips that I have shown in the previous slides can be just removed from the PCB, then placed into a programmer or a flash reader, writer, whatever. And then you can just extract the whole firmware image, which is like a hard disk for an desktop PC, and extract it and try to emulate it. And there's all information inside that you need to run the firmware. We have a small project, which is the SEC Consult Extractor, so the SEC Extractor project, which is on GitHub. The hardware and the firmware can be downloaded and compiled there. So yeah, you have to order the hardware at a PCB shop, for example, but the firmware is just C code, and yeah, that's it. And yeah, we are planning to improve the project a little bit when all of this COVID crisis is over, but let's have a look a little bit later. You can extract firmware by doing sniffing on the bus systems, for example, on the SPI bus, on the I2C bus, and so on. And you can also do it via side channel attacks or by using microscopy. But yeah, that's a big rabbit hole, and when you want to go down, you can do it. But I think that's a topic which will be covered in the last talk today, or is it a lab session where more hardware hacking is covered. And yeah, there are a lot of ways how to extract firmware from an embedded device. So as I started with this emulation feasibility study, I have first of all read about publications which were done in the past about multi-architectural firmware emulation. And I've seen two major projects. The first one was automatic dynamic analysis at scale. And that was a case study from Kostin and other researchers. They were using standard Debian images, which you can just download from the Debian site, and used a change root to change the root into the target firmware and execute firmware, binaries from the firmware and other stuff there. And I think they have also used a lot of automatic scanners to scan the running image from the outside. And yeah, they have done it with Debian images. So there are a few. They are more or less maintained. You can look on the website. And yeah, the problem is you cannot do a lot of things with the kernel, because you would need to rebuild the whole system, and yeah, that's not really possible for a precompiled image. Then there's also a project called Firmware, which is also really nice, and I think it's also on GitHub. They are using modified kernels with the muzzle libc and use the target the firmware file system of the target firmware directly for booting the whole system. So that's also nice, but the thing is, you have to do all the monitoring, the debugging, and so on. You have to do everything via QEMU and the kernel itself, and everything which is inside the target firmware file system, all the analysis tools. You don't know what is inside. Maybe the vendor has built in more, maybe the vendor has built in less. And both projects are apparently covering ARM and MIPS. And that are just two architectures, so ARML and MIPSL or MIPS Big Endian. And I wanted to do more emulation. So I've combined these two approaches, so the change root into the target file firmware with by using a own analysis image, so own kernel, own file system with tools, GDB and whatever, and then change root into the target firmware and the modified kernels. And for this, I used BuildRoot, which is the handy tool, the tool that you can use to develop firmware nowadays. So first of all, before you can emulate it, you have to do some preparations, which include finding out where the root file system of the firmware is located. Also find out which architecture and instruction is used. So the instruction set is really crucial because ARM instruction set 4 and ARM instruction set 7 is not really compatible, so in both directions. And you have also to find out which C library is used. So there are different C libraries. The most common C libraries I've seen are mucilibc, muzzle, and glibc. And that's also really important to find out which C library is actually used, but I will cover that a little bit later. And you have to prepare a system startup script, which includes all the startup scripts which are used during the boot up of the firmware. The first binary or the first script which is started is usually part of the bootloader argument, which you don't have when you just download the firmware from the internet. Then you may just have a partial image. Then you don't really have all the boot up scripts, maybe just a part of them, just 3 of 10 boot up scripts. And then you want to compile your own boot up script, which covers the parts which are at least present in your firmware that you have downloaded. So the first is locating the file system, the rootfs. I have thought, okay, that must be really complex to solve, but no, it was easy. Just do it graphically by using a keyword search. So I have just, I think I have written it in 20 lines of code, script code. You can just compile a keyword array, USR, SBIN, bin, etc, and everything that you know from a Unix-based or a Linux-based system, and then you just count the lines up to the name of the keyword, how often they occur. And when you have found the folder, this one which is UBFS in this case, which contains the most keywords, then this one may be your root file system. Sometimes there are more root file systems than just one. That yeah, that's a thing when there are rescue partitions, for example, and sometimes it's a little bit more complex because the whole embedded system is using multiple partitions, and yeah, then you will get a little bit lost, or you just copy it manually together. That's a little bit hard, and one thing that I have not solved until now. But yeah, as usual, it's a research project. So yeah, you can also use plausibility checks, like are there even executables in the /bin/sbin or whatever folder. If this is not the case, then it may be not the right root file system, or the files are maybe decompressed and are just lying around in the top folder. One word for decompressing. I've used binwalk -me for decompressing all the stuff. So I think most of you know this tool. It's, I think, the best tool that you can use for decompressing such firmwares of embedded systems. But yeah, I've just used binwalk, and for most of the firmwares, it works really good. Yeah, and one important message: do not rely on binary names like busybox, bash, ash, sh. Sometimes there are different names. For example, I've seen CLI or TC CLI or different names, which are just a bash, and they are just renamed. So this kind of search is a little bit better. I have also a histogram where you can see that two different root file systems are detected, and in this case, the slave root file system was detected because it had 18 hits, so 18 subdirectories, and the other one, which is the actual root file system, just had 17 hits, so one hit less. And yeah, but the thing is, you can compile the whole emulation firmware with both of them. So first with the first detected one, then with the second detected one. And yeah, that's really cool because you have multiple candidates. So identifying the architecture is another really important step during the whole process. So using readelf or file is really good. So readelf -a can give you a lot of information. So also the CPU name, the architecture, maybe whether it is using a vector floating point or not. But looking for the ver magic string in kernel modules can give you a really precise information, because it's often filled with with everything what the compiler was using. And yeah, there you see whether it's ARM, which instruction set, is it using vector floating point or not, sometimes even kernel versions and so on. And yeah, sometimes you can also find nothing about ver magic in kernel modules. Sometimes it's just empty. And there you can search for keywords like ARM7 TDMI or MIPS 32R5, some keywords depending on which kind of instruction set or which first fingerprint you get from the executables with file. And then you can refine the search for strings, for symbols, for whatever. And when everything fails, I have used this approach too for just one or two firmwares in the whole sample set. Then you can just grab all executables regarding ARM, regarding MIPS to find which instruction set is used. It worked for 2 cases, but yeah, it's a really bad success rate. So yeah, the instruction set matters. It's really important. Libraries are also relevant. Not that relevant. So you can execute binaries, for example, just static compiled binaries without knowing the exact library, because when they are static compiled, they won't use a lot of dynamic libraries. But for executing exploits, for example, on glibc or on other libraries in the firmware, you need to know it, because then you can choose the right compiler with the right library, the right loader, and yeah, then you have the right mapping and can use the exploit against the libraries. And sometimes it's also really crucial, for example, for ARM hard float or not, because then you have to modify the kernel what you're starting up with QEMU, and yeah, that may differ a lot whether you are using hard float or not, because then you can just execute binaries in the firmware or not, and that's really important. About the script preparation, which I have mentioned before, I have just looked for all the startup scripts at different places in the firmwares that I have dissected, and they are totally different, because sometimes they are placed in /etc, sometimes they are placed in /etc_RO, sometimes they are placed in another partition. So it's really hard to get all the startup scripts from the firmware into one startup script that you are firing up until when you are booting the firmware. And yeah, that is really hard until now. So nowadays I have cases where the firmware cannot boot because this really common startup script, which is placed in just another partition, is missing. So copy it and it works. So manual tweaking is always a big thing that you will need for firmware emulation, but yeah, it is how it is. And the best typical startup pointers are /etc, RCS, or init.d, or whatever. So for the system 5 specification, and for system D it works a little bit different, but all in all it's the same approach. You just look through the whole image and look where you can find startup scripts, and then you just copy it in your own startup script and place that in the firmware which you prepare to boot up the target. I've also done this evaluation of the whole sample set of almost 200 firmwares across all the vendors. I've found a lot of different combinations of interpreter, of architecture, of whatever. But you can see the musclibc and the libc. These two libraries are the most used libraries across all firmwares, and others are libc hard float, musl, and musl hard float, but just a few. And you can see when you count all these libraries together, it's more than 200 or more than 199. And the reason for that is that sometimes multiple libraries are used. So sometimes vendors have used SDKs, have used own code, then they have compiled their own library, copied the library from the SDK to execute the binaries from the SDK, and to execute their own executables, they have just used another library. And that's why you have more than more than these 200 firmwares, more libraries than these 200 firmwares are. And when you look at the architectural distribution, you can see that ARM is very often used as a little endian, but not the same for MIPS. So that's one of the reasons why the projects that I have previously mentioned, Firmware and the other thing for firmware emulation of Costin, that's why these projects were focusing on ARM little endian and MIPS big and little endian, because these architectures are very often used, and yeah, that's the I think the most architectures that I have seen. And when you look on the other special architectures, for example, MIPS 64, big endian, it was always, in 3 cases, Cavium Octeon, so from Cavium Networks, special MIPS processor. And I found documentation about that on a website where I have placed the links here. Maybe after my talk, these links will be not reachable because they hear about that. So I have saved it to the Internet Archive. You can also find them there, and the documents will be available. And that's why I have done this. Cavium Octeon is one architecture which is not integrated in QEMU. So there is no possibility with QEMU to emulate it, but it's integrated in KVM. So there shouldn't be a lot of work. Maybe it will be a lot of work. I do not program on this project, but maybe it's not that much work than integrating a completely new architecture in QEMU. And other special architectures are AVR and ARC5. I've also seen some firmwares there, but yeah, that's really just a little part of the whole sample set. So to build up a whole fake image, build root is very handy, as I have mentioned multiple times. The pre-analysis of the target firmware is now done. So now we can create a suitable firmware image and a kernel and a userland for analysis with strace, ltrace, GDB, and other tools. So you can see a screenshot of build root here. You can configure anything. So it's really easy to do. But you have to know a little bit about build root. So when you work sometime with this framework, yeah, you get comfortable with it, and then you can build firmware really easy. And for security analysis, cross compiler can also be generated automatically with build root, which is really cool, because then you can just build your exploits immediately with build root and try it on the target firmware. That's really nice. So you have a lot of dev configs, which are the templates for different architectures, for different systems that you want to build, and also for QEMU, which is really nice, because you can just use the dev config for QEMU, modify it a little bit, and then you can just emulate ARM firmware or MIPS firmware, and really fast. So it's not a lot of work that you have to do, but you have to get a little bit comfortable with build root, then it's not a big deal. So copying the identified root file system that we have done in the pre-analysis is really straightforward. You just create a subdirectory, copy it in there, and yeah, that's it. After that, you can start the firmware image by using change root, and then you can switch into your target firmware where you want to do the analysis. And yeah, running all startup scripts may be hard. It is hard finding all of them, but yeah, when you when you don't find all the startup scripts, you can just grab that, what you find, boot it up, and yeah, it's better than nothing. So you have fun while running partial, as you can see in this picture. The architectures that I have covered during the project are ARM32.5 big endian, ARM32.5 little endian, and so on. So a lot of different architectures. And you can also see on this picture also PowerPC Super H, and for example the 32-bit Intel processors, which are nowadays also used for embedded systems, which is really funny because yeah, a decade ago we have used it on our PCs. But yeah, and yeah, the target firmware image that I have found, or all target firmware images that I have found, was directly integrated into the firmware that I have built with build root. That's a little bit different to other projects because I've seen other projects where it was mounted via NFS, which I have also done in the beginning in 2017, 2018, but it's not really optimal for monitoring, for debugging, because when you look at the network traffic, then you will see a lot of NFS traffic going back and forth, and yeah, that's not really cool. Also, when you disconnect from the network, then the target file system is immediately gone, and yeah, what do we do then? I don't know. So I have just integrated the whole firmware image that I want to analyze into my build firmware image into my in my compiled firmware image, and that you have just a standalone image that you can just emulate on any PC where you have QEMU. And you can also change the networking config and so on via the command line. And yeah, loading kernel modules is a problematic thing because the kernel must fit for 100%, but that's another thing. So have a close look onto the emulation stuff. So that's, for example, the interface of build root, where you can see which parameters you can modify, but I don't want to go into much details there. I've prepared 3 firmwares, so Moxa, TrendNet, and Netgear, which I have started previously. And there you can see just the emulation of the Moxa device, where I can log in and see how it runs. So really smooth. That's one of the Intel processor stuff. And yeah, there you can also just change networking config and do whatever you want to like. You can also pen test these devices, of course. I have also done an ESO scan on one of these devices, and I have found cross-site scripting in I think 3 different endpoints. Not for this Moxa thing, but for another industrial device. And yeah, also a device from TrendNet, where you can also log in and look at the settings and so on. And yeah, some devices just run partial, as mentioned before. And that's, for example, this Netgear device, which is running a web server. You can see it here, HTTP, and is running, it is running a PowerPC CPU. And this device is not really serving HTML or HTML files, but you can find GIFs which are in the web root, And you can also reach CGI endpoints and so on, where you can download protocols and whatever. So it's just running partial, and you can test some things, but not everything. You can also look at the networking config, at the open ports. There's a lot of UDP and TCP. There are a lot of UDP and TCP listeners, and yeah, it's interesting which processes are running there. And I have also found for other devices, segmentation faults that you can trigger, or denial of service vulnerabilities for different processes, not just web interfaces. But yes, I've also prepared a little bit of output when you use readelf. There you can see that that's one of the Devolo devices, that this is from Arc, or how you can grep for the Vermagic string, which is not really present in the libraries, but sometimes in the kernel modules. You can see that here. And yeah, I have also one device, which is from Phoenix Contact, where I want to show you how the device boots up. So that's just the analysis VM that I will start now. You can see how it boots, and yeah, it will try all the exploits that I have integrated in the whole system, and then it will restart the networking stuff, because some devices are adding routes where you cannot reach the device afterwards. And yeah, that's a little bit painful, because you see open ports, but the routes are set in that way that you cannot access to the device via the web interface, and yeah, that's not cool. You can see there were some mod probe commands in the script, which did not work because the kernel version is different, because I have compiled an own kernel version with build root, but you can compile a different kernel version so that some of the modules get loaded and some will crash. But yeah, that's the thing on emulation. And now I think it's booted. It has the IP address 108. So yeah, and that's one of the routers from Phoenix Contacts. Yeah, it's really nice, because you can just pen test the device without having the actual device. Let me switch back. And yeah, monitoring and debugging is really nice with process monitoring, PS, netstat, TCP dump. You can look at the network traffic, which is sent from the device to some services on the internet, maybe. And yeah, there are other things, but I think you know how to use strace, ltrace, vol grind, and so on. And you can also use these tools on the analysis VM, where you host this target VM. And yeah, that's really nice. That's really comfortable, and you can observe the whole behavior of the emulated firmware. Yeah, from sitting next to the running image. That's really cool. The study samples were from different vendors, from industrial vendors, from network camera vendors, and so on. And yeah, you can just have a look at the slides afterwards. The outcome of the whole study was that 89% were emulatable in terms of executing the HAL, so the shell or bash, busybox, ash, whatever, and executing binaries. I've tested this by executing bash and writing something into a file, and 16% of all of the images were spawning a TCP listener, 8% were spawning an UDP listener, and yeah, some of the images were not complete, as I have mentioned at the beginning of the talk, because yeah, the vendors just provide you a partial image, and then you cannot start everything because configs are missing, executables are missing, and so on. And the known vulnerabilities that I have tested during the study were get address info, buffer overflow, ghost, and shellshock. Shellshock was just present in one firmware, and yeah, ghost in 14% of the sample set, and get address info just in 4%. But for, I think that the age of the CVEs 215, that's really old in images that are just from 2020 and 2019. That's painful, but it is how it is. I have one more demo, but I think we're running out of time. You can click on this link, so it's clickable, and you will get the slides afterward. It's just a command injection in a Phoenix contact device, which were communicated to the vendor and which is already published. It's really easy, just appending ./ls./ and then you see a list screen output. And we have also some unpublished advisories which are currently pending with the vendor Red Lion and Cornix, and they have also a lot of vulnerabilities, but it is currently pending in our responsible disclosure process, and a lot of more vulnerabilities that must be communicated, but where we had no chance because of a lot of internal tasks that were done in the last weeks, in the last 2 months, because of the crisis of the Corona stuff, And yeah, I wanted to show this demo live, but I have also investigated the command injection of the Phoenix contact devices with Ghidra. You can see that in line 162, the run shell function is called, and it just takes the input, runs it, and prints it to the screen, the HTML output. And yeah, that's one of the vulnerabilities which were really easy to spot. And yeah, it's really nice with Ghidra firmware reverse engineering, but I think you will hear something. Yeah, you will hear a little bit more later this day about that. So what are the conclusions? Firmware emulation with QEMU and Buildroot is really nice. So it works really good for some devices which are complete or where the firmware image is complete. And yeah, the approaches that I have tested, I have mentioned it before, precompiled images, building everything from the scratch, that's really painful. I don't like that. I'm too lazy, to be honest. And yeah, using the targets firmware file system only is not really comfortable because of you don't have a lot of tools, and observation is also not that easy. And yeah, manual testing is really hard. So I've done it in this way. And what are the improvements? You can implement KVM Octeon to QEMU. So KVM already exists. You can also add kernel hopping, where you just switch the kernel sources on Buildroot, which version should be compiled so that you can load kernel modules. That would be really nice, but it's a big task because compiling the kernel on my laptop, it takes 30 minutes, and yeah, that's not that cool. And you can also implement library resolving when all of the files get spread on the top folder. Then you can build up the tree by resolving the dependencies, for example, by using scanelf. You can reconstruct the whole file system by using that method. And you can also pre-emulate it by QEMU system emulation or QEMU user emulation for a better architecture detection. So that's it from my side. Thank you that I got the opportunity to speak on this live stream, and yeah, back to you.
Yeah, because we have run out of time. If people wanted to contact you, what is the best way for them to do so?
Email and LinkedIn.
Oh.
LinkedIn, you can find me really easy. So it's the same picture that I have used for this presentation, and yeah, email. But I don't have Twitter. So
okay.